The 2024 technical report is titled Qwen2-VL, Enhancing Vision Language Models' Perception of the World at Any Resolution. Those last three words make a broad claim, and that is what we need to test. Many earlier vision language models began by fitting every image into one fixed size, often 224 by 224 pixels. Take this tall document full of tiny text. Fit the whole page inside that square, and important details can disappear before the model starts reasoning. Qwen2-VL lets the grid of image pieces grow or shrink with the image. A larger grid takes more space in the model's input, and GPU memory still imposes a bound. Here, at any resolution means variable resolution within that bound. We will follow one image as the model turns it into visual tokens. The pieces pass to the language model. From there, we add positions in space and time, extend the same path to video, inspect the training process, and judge the two design ideas using the paper's own experiments. We start with a 224 by 224 image because its token count is small enough to check by hand. The paper says this image becomes 66 tokens before the language model, so let's check the count. Qwen2-VL sends it through a vision transformer, or VIT, with roughly 675 million parameters. The VIT reads the image in patches, small squares that are 14 pixels wide and 14 pixels tall. Since 224 divided by 14 is 16, we get 16 patches across and 16 down. Each patch becomes one VIT token, so 16 times 16 gives 256. Now let the input expand to 448 by 336 pixels while each patch stays 14 by 14. The grid grows to 32 patches across and 24 down, which makes 768 VIT tokens. Qwen2-VL makes this variable grid possible with 2D rope, a row and column position rule that replaces the VIT's learned absolute positions. A merger layer now compresses each neighboring 2x2 block into one visual token. 4 become 1. On our original image, the 16 by 16 grid becomes 8 by 8, or 64 visual tokens. The model places one start marker before those 64 tokens and one end marker after them. These markers tell the Qwen2 language model where the image span begins and ends. 64 plus 2 gives 66 tokens entering the language model. Apply the same merger and markers to the 448 by 336 image, and its 768 VIT tokens become 192 visual tokens, then 194 tokens for the language model. After patching and merging, the image dimensions determine how long the visual span is. A larger grid can retain finer spatial detail, and it also uses more sequence length. Those changing grids now need positions that still mean the right thing for text, images, and video. Take the 64 visual tokens from our first image. They are ready for the language model, but one left to right position only marks a token's place in the sequence. It does not separately mark its row and column. Inside the language model, Qwen2-VL uses 3 position IDs, T, H, and W, for time, height, and width. The paper calls this multimodal rotary position embedding, or M-ROPE. For text, the 3 IDs all copy the ordinary token position. Position 0 becomes 0, 0, 0. Position 1 becomes 1, 1, 1, and position 2 becomes 2, 2, 2. With matching values in all 3 slots, M-ROPE behaves like ordinary one-dimensional rope for text. For an image, time stays fixed while row and column change. If we start a small grid at 0, its top left token is 0, 0, 0. Move one step right and only width changes, giving 0, 0, 1. Move one step down and only height changes, giving 0, 1, 0. Video keeps that row and column pattern inside each frame. Now, time changes. In our 3-frame example, the same token at row 1, column 2 is 0, 1, 2 in the first frame, 1, 1, 2 in the next, then 2, 1, 2 in the third. The row and column stay fixed, while the first number identifies the frame. M-ROPE gives the language model one position system for text, image grids, and video grids. The paper stops at the coordinate rule. It does not disclose how the rotary channels or frequency bands are divided among T, H, and W, so the report alone is not enough to reproduce the exact M-rope implementation. Those time-indexed frames still need to pass through the shared vision encoder. Those time-indexed frames now enter the vision side. The paper says Qwen2-VL samples a video at 2 frames per second, so neighboring sampled frames are half a second apart. We take one grid square in a sampled frame, then the matching square in the next frame. A 3D convolution with a depth of 2 reads those 2 patches together as a short temporal tube. That lets the shared vision encoder receive information from 2 frames at once. A still image has no next frame, so Qwen2-VL duplicates it into 2 identical frames. That pair passes through the same 3D convolution and the same vision transformer as a pair from the video. During training, each video must fit within 16,384 tokens. Qwen2-VL adjusts the resolution of its sampled frames to stay within that ceiling, but the paper does not give the rule that trades clip duration against resolution. With this bounded input path complete, the next step is teaching the vision and language parts to work together. We now have a shared input path for images and video. The paper describes stage 1 as training only the vision transformer, while the language model keeps its starting Qwen2 weights. Across about 600 billion tokens, the training focuses on image and text relationships, text inside images, and image classification. In stage 2, every parameter is unfrozen, meaning every set of weights can change. Qwen2-VL trains the full model on another 800 billion tokens, bringing the 2 pre-training stages to 1.4 trillion tokens. That 1.4 trillion count includes image tokens and text tokens. The paper applies the training target only to the text tokens, while the image tokens provide context for predicting the text. Finally, Qwen2-VL locks the VIT and fine-tunes the language model on instruction data. These are conversations where a request may contain text, images, documents, or video, and the model learns to answer it. The report leaves 3 practical gaps in the training description. It does not resolve whether the visual merger changes in stages 1 and 3, gives no proportions for the data mixture, and omits most optimizer and compute settings. With those limits visible, we can turn to a narrower test, whether variable image token counts helped on the paper's reported tasks. The paper's first test compares 5 ways to feed images into Qwen2-VL 7B. 4 use a fixed budget of 64, 576, 1,600, or 3,136 image tokens. The 5th lets the token count change with the image, and it averages 1,924 tokens. When we read across the 4 tasks, the 3,136 token fixed setting leads InfoV-QA and real-world QA. The dynamic setting scores highest on OCR bench and ties the best MMU score. No fixed token count wins all 4. Compare dynamic with that 3,136 token row. Dynamic averages 1,924 tokens, 1,212 fewer than the fixed row, or 38.6% less. Its scores on InfoV-QA and real-world QA are lower by 1.38 and 0.52 points. The second test takes small images and enlarges them until they meet a chosen minimum size. On OCR bench, the curve reaches its high point near 280 by 280 pixels, then drops as the minimum rises to 560, 840, and 1,120. Past that point, forcing more pixels made the result worse. We cannot tell whether the 5 settings came from separately trained models or from different resizing at evaluation. The report also gives no running time arithmetic work, memory use, or spread of token counts across images. The 1,924 figure supports an average budget comparison, while speed and memory remain unmeasured. For these reported tasks, the evidence favors adapting the image budget over pushing every image toward one large setting. We can now judge MROPE by the same standard. For MROPE, the paper gives us a direct side-by-side table. It uses a smaller Qwen2-1.5B plus VL backbone and reports 1D rope beside M rope across 11 tasks. 8 rows use images and 3 use video. On the image side, MathVista rises from 39.2 to 43.4. Real-world QA falls from 54.5 to 53.7. And InfoV QA falls from 50.8 to 50.3. Across all 8 image rows, MRope is higher on 5, equal on 1, and lower on 2. The 3 video rows are more consistent. Perception test moves from 46.6 to 47.4, NEXT QA from 43.9 to 46.0, and STAR from 55.5 to 57.9. MRope is higher in all 3. The table gives one number for each setting with no repeated runs or measure of how scores vary. That matters most for changes of a few tenths. From this table alone, we cannot tell whether those small differences would hold across reruns. The paper's separate test uses Qwen2-VL 72B on video MME medium. Each training video was capped at 16K tokens. When the allowed inference length rises from 32K to 80K tokens, accuracy stays between 70.4 and 71.3, with 71.1 at 80K. On this test, the curve stays stable as the allowed limit moves beyond the training ceiling. The plot contains only the M-rope model. A matching 1D rope line is missing, so the stable curve leaves M-rope's causal role unresolved. MRope's clearest direct support comes from the 3 reported video task gains. With both design choices checked against the paper's evidence, we can return to the words "at any resolution." Those words bring us back to the tall page from the start. Qwen2-VL can keep its visual grid tall instead of squeezing the page into the same 224 by 224 square as every other image. A small image gets a smaller grid, while a larger image gets more visual tokens. This is what "at any resolution" means in practice. Before Qwen2, the 2x2 merger turns each group of 4 neighboring patch tokens into one visual embedding. In our 224 by 224 example, 256 patch tokens became 64 visual embeddings, then 66 tokens after the 2 boundary markers. A larger grid is compressed the same way, so it still creates a longer visual span. MRope then assigns time, row, and column coordinates across text, image grids, and video grids. Text advances all 3 together. An image varies across row and column, and a video varies across time as well. With those positions attached, the visual embeddings become a span the Qwen2 language model can read beside text. The report gives us enough detail to reconstruct the token count for a 224 by 224 image and trace the path it discloses. Its own ablations give dynamic resolution and MRope qualified support. Reproducing the full system still requires exact preprocessing, MRope parameterization, and the complete training recipe. With the whole path back in view, at any resolution has a precise meaning. Qwen2-VL accepts varied resolutions and aspect ratios by changing the visual grid and token count within pixel and sequence limits set to fit available memory.